Good day, dear friends. My name is Evgeny Proskrin. I'm the founder of ATF Group. This is an engineering and manufacturing group of companies that started in a garage, producing hardware for transformers. And now it offers digital solutions for a wide range of industrial sectors. Today we are launching a series of micro lessons to share practical knowledge and help our energy sector operate more reliably, efficiently, and safely. After all, our mission is simple: your energy under our protection. In the previous video, we explored how impulse over voltage distributes along transformer winding turns and why the first turns experience maximum stress. Today, we will dive deeper into the wave nature of the impulse. We will examine how voltage propagates along the winding, explain the concepts of traveling and standing waves, and describe how harmonic analysis represents the impulse. The transformer winding is a distributed system characterized by inductance per unit length, capacitance between turns, insulation resistance and conductance. When a steep impulse occurs, a voltage wave travels along the winding at a certain speed, reflects from the winding end depending on grounding, interacts with the wave traveling in the opposite direction. Any impulse can be decomposed into a Fourier series of harmonics. Each harmonic propagates at different speeds. Higher frequency components result in faster rising edges and higher voltage gradients, boundary conditions. If the winding end is grounded, O reflection occurs with an inverted phase. A standing wave is created. If the winding end is isolated, O reflection occurs without phase change. O voltage amplitude doubles at the end. The wave behavior depends on winding length, distribution of capacitance and inductance, load resistance. The wave equation models the voltage wave. Its solution involves two arbitrary functions representing the incident and reflected waves. The superposition of these waves forms either standing or traveling waves. Practical example: impulse voltage of 250 kilovolts with a rise time of 1.2 microseconds. Winding length of 1.5 meters, dielectric permittivity given. Wave propagation speed calculated accordingly. Time for wave to travel full winding length determined. The impulse reaches the winding end almost instantaneously, causing reflections. When incident and reflected waves combine, at nodes, voltage reaches a minimum. At antinodes, voltage peaks increase by 1.5 to 2 times. This explains voltage amplification in the middle of the winding during frequency resonance. Practical analogy: the winding behaves like a stretched string. Striking it generates waves traveling back and forth, forming standing wave patterns. Higher tension or inductance leads to faster waves and stronger resonance. Practical task: for a winding 2 meters long, calculate the impulse propagation speed. Determine the time for the impulse to reflect from the end and return to the start. Draw a standing wave pattern with 3 nodes. Today we learned how impulse voltage propagates as waves, how to decompose it into harmonic components, what standing and traveling waves are, and how they influence voltage distribution. In the next video, we will explore how engineers calculate winding behavior under complex conditions by using matrices of capacitances, inductances, and external connections. This approach bridges theory and practical design and protection of transformers. Want to explore the topic in more depth? Visit our website. The link is in the description. Interested in real-world solutions and industry challenges on this topic? Contact us. Our details are on the screen. Want to become a part of the global energy flow? Reach out to us. You'll find our contacts on the screen.